We're doing experiment 5, analysis of a KClO3 mixture. And so you should take a look at this experiment before lab. So it's a mixture of KClO3 and KCl. And so the purpose of this experiment is to determine the percent KClO3 in this mixture. And we're going to do this by reaction, a chemical reaction. It's going to be the decomposition of a KClO3. KCl won't decompose, so it's stable. But KClO3 is kind of reactive. So we're going to decompose the KClO3 solid using some manganese 4 oxide as a catalyst. This delta symbol here means heat. And that generates KCl and oxygen. And by collecting the oxygen gas, we can use stoichiometry to figure out how many grams of KClO3 were in our original mixture. But we're going to collect the oxygen gas over water. So it's not going to be pure. It's going to be wet oxygen. And so the pressure of the wet oxygen is equal to the pressure of the dry oxygen plus the pressure of the water vapor. And so if we want the pressure of the dry oxygen, we'll have to subtract the vapor pressure of water from that. And so this is kind of what we were looking at yesterday. But that's a Dalton's mixture. The first part of this lab is going to be an Avogadro's mixture. And so I'll talk about this when we start the lab on Monday. But take a look at it. Today what I want to do is I need to finish up chapter 6. So I'm going to finish up chapter 6, and I'm going to probably post a video lecture on starting chapter 7 so we can get kind of caught up again for the weekend. So take a look at the video lecture. I'll post it tomorrow. All right, for gases, I went back and I looked at the equations here. So let's take a look at these. So this is the Maxwell-Boltzmann equation here. This equation describes the distribution here. So this is just the equation modeling the distribution here. In the thing, we're not really going to be interested in the mean nor the average. We're just interested in the RMS. In the RMS, we aren't actually going to calculate it like this, but the RMS is if you take every speed, and there's a lot of speeds here. If you take every speed and square it, and then average the squares, and then take the square root. That would be the root mean squared. But, you know, what does it mean when you do that? And from statistics, what it means is this. It means that if you were to slow down all the fast molecules and then speed up all the slow molecules to give them all the same speed, so this would be like the equity, you know. Equity would be to cut down the top and then bring up the bottom. And so everybody's the same. And so these would be all identical. And if they were all clones of one another, then we would have the RMS. And so we call this the effective speed of the population. And therefore, we can treat the population. This is just for calculations. Why would we want to treat the population as having just one speed? Well, the reason we would want to treat the population as if it's having one speed is to make energy calculations easier, because when we do energy calculations, we're going to get a distribution of energies as well. We're going to get energies up here and energies down here. What we want to know is the effective energy of the population. In other words, we want to know what's called the average kinetic energy of the population. So we aren't ever going to calculate the mean nor the average. We're only going to calculate the RMS speed, the effective speed. This is the equity speed of the population. So we did that, and we did that for oxygen. And if we have a sample of oxygen at 0 degrees C, 0 degrees C is not very useful, I think. 25 would be more useful, room temperature. But if it's at 0 degrees C, it's moving about 1,000 miles an hour. And the hydrogen, since it weighs twice as much, but it's a little bit tricky because we'll have to square root the difference in the molar mass. It was 4 times. Actually, oxygen is 4 times heavier, or 8 times, oh something. So the speed of the hydrogen, since it weighs a lot less, is a lot faster. But still, we have slow hydrogens and fast hydrogens. What's happened is the distribution's moved up. And we don't describe the distribution by this peak. We describe the distribution by the RMS. The RMS is on the shoulder here. So you can see that what happens with lighter molecules at the same temperature is they move a lot faster. They're here. So hydrogen's over 2,000 miles per hour, which is faster than the speed of sound. So it's up here. We can heat up oxygen. This is oxygen at 273. If we heat up oxygen, the distribution moves over. The total population stays the same, so that's why the curve shrank. But because we're just spreading it out further up to higher energies, higher and higher energies. And so we are going to do some calculations with this distribution later, but for right now, we're just looking at the RMS. So what we have here is this symbol, E bar. You know, E stands for energy, and the subscript K, you know what the K stands for? It stands for kinetic. And the bar means average. And so here we deal with average. We deal with average energies. The average kinetic energy is equal to 1/2 m. Okay, this is saying average, but this is not entirely correct here. This is going to be 1/2 m URMS squared here. And so let's do that here. And so I'm going to calculate this is the average kinetic energy. And I'm just going to make it a little bit simpler. We're just going to call this 1/2 m URMS squared. And this is where m is the mass of a single particle, mass of the gas particle. I'm calling it a particle because it could be an atom or a molecule, so I'm not going to call it a mass of a gas molecule. And URMS is the root mean square speed, and we have to square that. And this gives us our average kinetic energy. So we just take the effective speed, and this comes from Newton's laws. Newton's law says that the translational kinetic energy is equal to 1/2 mv squared. V is the velocity. And so there's different symbols that are used. V equals velocity. That's normal, except we're using U. So Petrucci likes to use U for velocity instead of V for velocity. And so we'll use U for velocity. But this is the velocity, RMS velocity. Velocity is just the speed, how fast is it going. This comes from, again, Newton's laws in physics. So this is the equation that we'll use to calculate the average kinetic energy here. And so if we want the mass, this is the mass of a gas particle in kilograms. Oops. And so the units would be kilograms here. So let's just figure out the E bar K for oxygen at 273 Kelvin. And so the mass of oxygen is 32. 32, what is it? Grams per mole. And then what we're going to do is we're going to convert it to kilograms. And then we don't want it per mole. We want it per molecule. So I'm going to convert moles into molecules. And then URMS we had just calculated, except I need it in meters per second. 461.3 meters per second is from our previous calculation. 461.3 meters per second. And then we square that. So when we look at the dimensions of this, the grams cancel, the moles cancel, and we end up with kilograms meters squared per second squared as the unit per molecule. So this is the energy per molecule. A kilogram meter squared per second squared is a joule. And so this is the joules of energy per molecule. And so we could go ahead and calculate how many joules of energy. Do you think it's going to be a big number or a small number? It's going to be a really small number because, you know, oxygen is quite small. So let's take a look here at this. 32 divided by 1,000 divided by 6.022 times 10 to the 23rd. Times 461.3 squared. Comes out to 1.13. This is 32.0. I guess we could go for sig figs. 307 times 10 to the minus 20 joules per molecule. And so very, very, very small number here. But if you have a mole of them, you know, then we would multiply this by 6.022 times 10 to the 23rd. And that gives us 6,809 joules per mole. You know, that would be the average kinetic energy. Now, why would we want to know the average kinetic energy? The reason we want to know the average kinetic energy is because the temperature is a measure of the average kinetic energy. So it says the Kelvin temperature of a gas is directly proportional to the average translational kinetic energy of its molecules. So T is proportional to EK. This is for an ideal gas, because the ideal gas only has translational kinetic energy. If we're doing a real gas, the equation is a bit more complicated because we'll have to add in rotational energy and vibrational energies to this, so the math gets more difficult. So there are some other things that we're interested in. One of the things is this. if the two gases are at the same temperature, so we have oxygen at 273 and hydrogen at 273, but you see the hydrogen's moving much faster on average or on RMS, if you look at the RMS speed. The hydrogen's moving much faster as a collection versus the oxygen. But they're at the same temperature, so they have the same average kinetic energy. So everything will have the same average kinetic energy if they're at the same temperature. So the air in this room is at the same temperature as the water. So the air in this room has the same average kinetic energy as the liquid water here, which will have the same average energy as the plastic here, which will have the same average kinetic energy as the table here. What's different is, how fast they're moving. The oxygens are moving at 1,000 miles an hour, or more than 1,000 miles an hour because it's a room temperature. But do you think the water molecules, how fast are those moving? Actually, the water molecules are moving pretty fast, but you have to look at the total, because oxygen will have rotational, vibrational, and translational, but the vibrational isn't so deep. Water has lots of vibrational energy, and so it's odd, but they have the same average kinetic energy. So anything at the same temperature will have. But why is the speed? Because the kinetic energy is dependent on the mass, and so the heavier it is, the slower it's going to be moving. The lighter it's going to be faster moving, and the velocity, the mass and the velocity. So if one goes up, the other goes down in order to have the same energy. Now, there are some other things that we can do. I just had a, let's see, not that. I just asked ChatGPT to do this calculation for me. You don't have to do this. This equation's not in it, but these are equations that come out of kinetic molecular theory. And I didn't want to calculate it. But, it was kind of qualitative in the book, how it says. So there are two things that we're very interested in gases in kinetic molecular theory. One of the things is mean free path. Mean free path is how far does a particle travel before it collides with something, on average. And so when we look at the mean free path, if the pressure is low, let's say the pressure is a microatmosphere, then the mean free path is about 6.7 centimeters. So at a microatmosphere, a particle will travel about 6.7 centimeters on average before colliding with something. That's a huge distance in terms of how tiny the particles are. If we go to 1 atmosphere, how far does a particle travel before it collides? 10 to the minus 8. 10 to the minus 8 is like 10 to the minus 9 meters is nanometer. And so about 0.6 or about 670 micrometers. So 670 micrometers, that's in air. Is that very far? No, but if you're a particle, a gas particle, that's considered a far distance. Let's say we go to 10 atmospheres. If we go to 10 atmospheres, then it's 6.7 nanometers. And if we go to 100 atmospheres, it's like 6.7 times 10 to the minus 10, so that would be 6.7 angstroms? No, not, 6.7 angstroms. You know how big atoms are? Atoms are on the order of hundreds of picometers. Hundreds of picometers. Picometer is 10 to the minus 12. So if we move the decimal over, that's 670 picometers. So there's very little room here. This is getting on the order of the size of the atom. Atoms range from 1 to 6 angstroms. This is 7 angstroms, roughly. It doesn't travel very far at 100 atmospheres if ChatGPT did the correction correctly. Okay, the other thing we're interested in is how frequent are the collisions. We call that the collision frequency. The collision frequency here is in hertz. Hertz would be collisions per second. And so at a microatmosphere, there's about 7,000 collisions per second. At 1 atmosphere, there are, that's a million, billion, about 7 billion collisions per second. And so this just kind of, the video that, the simulation that I showed was slow motion because, when we're at, let's say, 1 atmosphere, we're expecting about 7 billion collisions in a second. There, it was slowed down so much. All right, from laws can come from either direction. What do I mean by that? Laws can come from, what's on the left side of the scientific method? Experiment, observations. We can derive laws from observations, or laws can come from the right side. The right side of the was theory. And so here, what they're doing is they're doing a derivation of Boyle's law using kinetic molecular theory. Boyle's law originally was determined by Boyle using experimental observations. But here we can use kinetic molecular theory to derive it. And so this is interesting, but you don't have to worry about this. And so they're just using the equations from kinetic molecular theory to do that. So I'm going to skip that. And then we've got 6.8 is gas properties relating to kinetic molecular theory. And so if I have hydrogen over here, nitrogen, and the barrier here, what happens if I remove the barrier? The gases will mix. That's what happens. And so if we remove the barrier, the gases mix. And now we have mixed gases. When I talked about driving forces for chemical reactions, the driving forces that I talked about were thermodynamic, energy related, So we're talking about, higher energies, less stable, lower energies, more stable. And so what types of things form more stable? This is kind of interesting because let's say the temperature doesn't change. Let's say we start off at room temperature and we end up at room temperature. If we start at room temperature and we end at room temperature, did the energy change? No, because the temperature tells us what the energy is, the kinetic energy. And ideal gases have no potential energy, so we don't have to worry about potential energy. And so the question comes up, what is the driving force for mixing? If we're not going from higher energy to lower energy, then why do the gases mix? We remove the barrier, but why don't they just stay where they are? Well, I mean, it's obvious. When you think of kinetic molecular, they're just moving, and so they're just going to move. But one of the things that we think about is we also have to consider something called entropy. And with entropy here that's what's driving this, the entropy. Entropy is going from a more ordered, this is more ordered, to a more disordered state. That's a driving force. And so we're not going from a less stable to a more stable, we're going from a more ordered to a more disordered state. Well, this is called diffusion here. And then over here, we could have a vacuum here, there's no gas, and poke a pinhole. If we poke a pinhole through there, then the molecules can effuse. This is effusion. The top is diffusion. So this is related to how fast they're moving. The faster they're moving, the faster they're going to diffuse and effuse. So if we look at hydrogen versus nitrogen, which one's moving faster? Well, the lighter one's moving faster. Hydrogen's moving faster. Hydrogen's going to be a lot faster than nitrogen. And so hydrogen's going to diffuse faster, and hydrogen's going to effuse faster. So this is going to leak hydrogen much faster than it leaks nitrogen. Then we have a simple law for this. It's called Graham's law. We could use this for both effusion diffusion. But the rate of diffusion of a gas is inversely proportional to the square root of its molar mass. So the heavier it is, the slower it moves. But it has this 1 over the square root of molar mass dependence. This is only for gases at low pressure. You know. Tiny orifice does not apply to diffusion. This equation doesn't apply to diffusion. This is just for effusion here. Diffusion has a complication. The complication with diffusion is, let's say somebody has some mint tea and they open it over here or drink it over here. Do the people on the opposite side of the room smell the tea instantaneously? No, it takes time for the tea smell to move over there. But you know how fast the molecules that give the tea smell move? The molecules that hit your nose and create the smell of mint are moving at like 500 miles an hour, URMS. If their URMS is 500 miles an hour, if you're traveling 500 miles an hour, how long does it take you to get across the room? Not even a microsecond, right? Maybe a microsecond or something? Shouldn't you smell the tea instantaneously? You don't smell the tea instantaneously because of this. Because of this. You know, if we're at 1 atmosphere, how many collisions are there in 1 second? 7 billion collisions? So as the tea's trying to make its way across the room, it's like it's a crowded room. Even though it doesn't seem like a crowded room, even though the air seems like empty space, that's a lot of collisions. So this is like if you tried to walk across a packed auditorium and there's only standing room only. It's going to take you some time because it's like a maze. You got to weave your way in and out of people. And the same thing, even though this is moving at 500 miles an hour, it's going backwards, sideways, forward, backwards. And so it's actually traveling a great distance before it hits the opposite side of the room. It's not a bird's eye flight. You know, if the bird had 7 billion collisions and traveling from here to there, it's going to take a long time for the bird to get anywhere. It doesn't slow down. That's the situation with the ideal gas is it does not slow down. It maintains its energy, kinetic energy. The difference between diffusion and effusion is diffusion's moving across a room, whereas effusion's leaking out of a pinhole. So when we leak out of the pinhole, we don't have to worry about 7 billion collisions occurring. It's just leaking out of the hole. When we do diffusion, it's more complicated because now, you know, as this one wants to travel to the opposite side, how many collisions is it going to undergo in getting from here to there? You know, its mean free path at 1 atmosphere is pretty small. I mean, if you think about it, if the mean free path is, what was the mean free path at room temperature? This is for kind of air at room temperature. So at 1 atmosphere, the mean free path is 10 to the minus 8. That is about 600 micrometers. So the mean free path is 600 micrometers before it has a collision. If you want to get from here to there and you're colliding every 600 micrometers, that's going to be brutally tough. You know? So diffusion's more complicated because we have to factor in the collisions and everything else. Effusion's quite simple. So the diffusion problems are all going to be qualitative. You know, if something's moving like twice as fast, then it should diffuse twice as fast. The effusion problems are going to be quantitative because the equation's simple. So, and most of the effusion problems are like how much faster does it effuse. So the rate of effusion is inversely proportional. And so we see the rate of diffusion of A is inversely proportional to the square root of the molar mass of A, and the rate of diffusion of B is inversely proportional to the molar mass of B. And so this is the equation that we use to do simple calculations, like how much faster does helium effuse versus nitrogen. And so is it 2 times faster, 4 times faster? Well, actually, we could just do that here. How much faster does helium fuse versus nitrogen? So helium's faster. So it's going to be the square root of helium's molar mass is 4. Nitrogen's molar mass is, let's do oxygen, 16. So this is helium versus oxygen. And so we see that oxygen is not 16, it's 32 because I have to multiply it by 2. And so it weighs how many times? It weighs 8 times more. Maybe I shouldn't have done this because now I have to do the square root of 8. I don't know what that is. So it's square root of 8 times faster. And so square root of 8 is equal to 2.8. 2.82. 2.82 times faster. So even though oxygen weighs 8 times more, it's not 8 times slower. You know, we have to do this kind of ratio with the square root. Square root screws things out for doing it easily. All right, this is the rate, and then this is the time it takes is inversely proportional. So the time it takes for B to effuse versus A to effuse is directly. So the faster the faster it is, the shorter the time. The slower it is, the longer the time. And so they're inversely proportional. So rate and time are inversely proportional. This is the time for diffusion. Derivation, I'm not going to go into the derivation. This is derivation from kinetic molecular theory. It's nice to have derivation in there, but I'm not going to do it. Okay, the last section of the book talks about non-ideal real gases and the deviations. Most gases behave ideally under normal conditions. What are normal conditions? Normal conditions is around how many atmospheres? About 1 atmosphere. And normal temperature. Normal temperature is about what? Room temperature, 25 degrees C. However, if you deviate from those, we have to worry about large deviations from the ideal gas law. The ideal gas law, when you calculate it, it predicts this. That is, PV over nRT is equal to 1. It's a constant. So PV equals nRT, so if you take PV divided by nRT, we get 1. That's called the compressibility factor, and so we know that 1 is for an ideal gas. But you can see it deviates here. So for example, for hydrogen, it automatically goes up here. In other words, the pressure and volume are greater than what you predict. Actually, we just look at the pressure in this case, or the compressibility factor. However, for oxygen and CO2, it drops. And so we get lower pressures than predicted. Hydrogen, we get higher pressures than predicted at higher. And so what causes these deviations? There are 2 things that cause these deviations, and we can model these. You know, the ideal gas law won't fit this curve, or this curve, or this curve. So we try to come up with an equation that fits these curves. And it's not a simple equation because the equation has to fit, you know, hydrogen, oxygen, all the gases. And so this is just one of the equations. There are other equations, the Villarreal equation. This is the van der Waals equation. Only the van der Waals equation is talked about in this book because it's more conceptual, you can see. So all we do is we take PV equals nRT and add some corrections for non-ideal behavior. The first correction is this variable A here. N is the moles, V is the volume, and this variable A means something. The second correction we make is this variable B here, where we have to correct the volume. All right, let's correct the volume first. B corrects for the size of the particle itself. Do you have a big gas particle or a small gas? The bigger the gas particle, the bigger B is. And the bigger the B is, the less empty space you have to move. The less empty space you have to move, what's that going to do to the volume? It's going to shrink the volume, which increases the pressure. And so if the particles are big, there's not as much volume and the pressure should increase as the volume decreases. Volume decreases, pressure increases. However, A is due to intermolecular forces. The stronger the intermolecular force is, the lower the pressure we have to be. We have to get. You know, as this term grows, the P has got to shrink in order to maintain the same nRT. And so the two things that screw up the ideal gas behavior are intermolecular forces and particle volume. And so we see the ideal gas here has no intermolecular forces. And so A, this is for intermolecular forces here. And so the weakest intermolecular forces will be helium. And the worst on this will be, looks like propane is the worst. Yeah. Propane is going to be the most sticky of the molecules listed here. It's easy to liquefy propane. It's hard to liquefy helium. And so liquid propane is not a big deal. You get that in your propane tank for the barbecue. And so propane is going to deviate from ideal behavior, but it's kind of weird because intermolecular forces decrease the pressure. However, propane's a big volume. You know, it's kind of a big molecule. And being a big molecule, it's going to cut down the volume, which increases the pressure. So one of these non-ideal factors decreases the pressure. The other non-ideal factor increases the pressure, and we're kind of close to break even. And so even with some deviations here, we get somewhat reasonable answers. So this is why when we use the ideal gas law, we'll just go ahead and use it for propane. If you're worried about it, then you use the van der Waals equation. You plug that in. And so we'll plug in A here, and we have to also have moles and volume in there as well. And then propane's kind of a big molecule. Do you see? It's the largest of all these. 1 mole of particles occupies a volume of about 90.5 milliliters. 90.5 milliliters for 1 mole, or 0.0905 liters. And it depends on how many moles. If you have 10 moles of that, that's actually quite a lot. That's almost a liter worth of particle volume. And then we have the compressibility factor. So doing this conceptually here, intermolecular forces are going to weaken the pressure here, you know, because the molecules are kind of sticky. So this is showing these three are holding this back from colliding forcefully with the wall. Particle volume screws things up as well. You know, if the mean free path were about the size of an atom, it's not going to move very far because atoms are in there and atoms exist. In an ideal gas, there's no particle volume. The volume of the particle, these are point masses that occupy no volume in an ideal gas. But in a real gas, the particles themselves are going to occupy it. So under extreme pressures here, there's not that much free space to move in. And so there's some calculations on using this. So all you do is just plug in. You know, you plug in your A here, your N here, your B here, your P there. Plug in the B. You have to do this for each gas because each gas will have a different strength of intermolecular forces, and each gas will have a different particle volume. So this doesn't work for all gases. Whereas the ideal gas law is PV equals nRT. Use it for every single gas. You don't have to worry about what the gas is. All right, any questions on this? There's some tutorial problems on using the van der Waals equation, so I'll leave the example calculation for you to do. All right, the next thing I want to do is switch over to redox. I want to finish talking about redox reactions. So I think the most probably the most used will be the chart method here. But we're going to go on and look at some other stuff too. So single replacement didn't work for copper and nitric acid, but the chart method does work. And so let me finish this slide since I didn't, looks like I didn't finish it. I thought I finished this one. And so we're going to add these two up. I'm going to cross multiply here. So I have 3 electrons here, 2 electrons here. So I'm going to multiply this one by 3. And then I'm going to multiply this one by 2. Let me make this more legible. And then I'm going to just combine everything. So I'm going to get 3 coppers solid plus 2 nitrates plus 8H plus 6 electrons yields 3 copper 2 plus 6 electrons plus 2 NO gas plus 4 H2O liquid. Then I'm going to look for a driving force. I like to have the half reactions here because this is oil or rig copper. This is oil. This is oxidation is loss. And if copper is oxidized, is it the oxidizer? If copper got oxidized, is it the oxidizer? No. This is the reducing agent. What was the oxidizer? The oxidizer was 9. And so this is the rig. This is the oxidizer here. And then we use the conjugate relationship. On the opposite, we have its conjugate oxidizer. So copper 2 ions would be the conjugate oxidizer. On the opposite side of this, we'll have our conjugate reducer. And so we're going from copper, our reducing agent, nitrate and H+, this is our oxidizing agent. Copper 2+, this is our oxidizing agent going backwards. And NO plus 4H2O, this would be our reducing agent going backwards. And then we use the chart to compare copper versus copper 2 ions versus nitrate and acid. So here we have nitrate and acid, or nitric acid, and here we have copper 2. Nitrate and acid is stronger oxidizer. So we go back over here. Oops. And we say that we're going from stronger oxidizer to weaker oxidizer, and that's our driving force here. Because of the conjugate relationship, the reducing agents have to be the same. And you could verify that, but that's it. So then, since we have driving force for this, I'm going to go ahead and clean it up. That is, I'm going to get rid of things that are on both sides, like the 6 electrons. Oops. Try to cancel those out. 6 electrons here, cancel out the 6 electrons there. And then that's it. So using the chart method, we end up with this equation here. 3 copper solids plus 2 nitrates plus 8H plus yields 3 copper 2 plus 2 nitrogen monoxide or nitric oxide gases plus 4 H2O liquids. This is already NIE. And so the chart method yields the NIE for this. I'm not going to work backward. You can work backwards to get the total ionic equation and the complete equation, but I'm not. Okay, so that was that. Let's try this one. Potassium solid is added to sodium chloride solution. This looks like single replacement. So if we were to use the single replacement says A plus BX yields AX plus B. So I would suspect I would form potassium chloride plus sodium. Sodium, this is the metal, not the ion, the element sodium. And then for single replacement, we consult the activity series. The activity series is actually here, upside down. And so this is our upside down activity series. So we have lithium's the most active, and then potassium. So we're comparing potassium and sodium. Which one's more active? Potassium is more active than lithium. I mean, not lithium, than sodium. Lithium's most active. So going back to this equation here, we would say we have driving force. The driving force would be going from the more active element to the less active element. So more active potassium to less active sodium. The activity series is based on, note, activity series is based on reducing agent strength. So when we do this, we're going from a stronger reducing agent to a weaker reducing agent, sodium being the weaker reducing agent. Unfortunately, this is wrong. Even though we do predict this reaction, this is wrong. It's wrong because what's the oxidizing agent here in the single replacement? What took the electrons from potassium? Sodium ions. It's wrong because there's a stronger oxidizer present than sodium ions. Do you know what the stronger oxidizer present than sodium ions is? Water. And so we do the chart method. For the chart method, we have potassium, we have sodium chloride, and we have water. And so the first thing is we inventory the major species. So inventory, the major species is potassium solid, sodium ions, chloride ions, and water. Those are the major species. And then we look at the chart. When we go to the chart, potassium only occurs on the right side, the reducing agent side. Sodium ions is on the left side, the oxidizing agent. Chloride ions is only on the reducing agent side, and water is both on the oxidizing agent side and the reducing agent side. And so it looks like we have two oxidizers. We have sodium ions and water. Which one is stronger, sodium ions or water? So we just go back to the chart and then just look it up here. Water, where does water belong? It doesn't belong at the bottom of the chart. Water belongs here between zinc and aluminum. So if we properly rank water here, then we can see, let me write that here. We can see that H2O liquid is a stronger oxidizer than sodium ions. And so why would sodium ions be the oxidizer? It doesn't make sense. There's a stronger oxidizer. That stronger oxidizer is water. And so we go back here, and then we select the stronger of the two. The stronger of the two is the more likely to react. It doesn't mean there's going to be a reaction. We have to look for a driving force for that. But if there were a reaction, then we expect water to be the oxidizer, not sodium ions. Sodium ions are weaker. Now we have three reducing agents, potassium, chloride, and water. So we'll go back to the chart and look at the reducing agent strength. So starting off with the strongest reducer, which is lithium, and then we'll look. We have potassium, metal, very powerful reducer. We have chloride and water left. So which one's better, chloride or water? So let's scroll up here. Here I have water, but I can't use this water because I don't have any sulfur dioxide. So I'll scroll up some more. Here I have water, but no nitric oxide, water, but no iodine. Here I have water. And so water is a better reducing agent than chloride. Chloride's the worst of these three. But an odd thing happens. Let me do this here. There's one exception in this chart. It's chloride versus water. Chloride wins. As a reducing agent. And the reason why chloride wins is an oxidizer only has to pull an electron off its outer shell. And so chloride's easy to oxidize. In order to oxidize water, you have to remove the electrons off oxygen and break the bonds, rearrange everything. It's not so easy. So even though you get more energy in return, sometimes nature takes the faster way. So it's something like this. Okay, what would you rather do? Would you rather get $100, like 50 years from now, or would you rather have $10 right now? what would you take? $100 50 years from now, or $10 right now? Probably $10, and that's kind of what nature does. It just will take the easy way. You know, this is called kinetics. Kinetics is, you know, eventually it might take the $100, but you know, when you have a bunch of collisions and things are happening, then that's it. And so, even though you can get more energy back by water reacting, it's just too slow. It's taking too long. And so chloride's fast, and how much more energy are you going to get? Let's say you could have $10 now versus $12 50 years from now. What would you take? Ignoring inflation, you know. Is it really worth waiting 50 years to get $2 extra? Yeah, I know. It might be all electronic. Who knows? But anyway, so this is it. So this is the one exception you need to know, that even though water is ranked as a stronger reducing agent, if you ever see a scenario of chloride versus water, chloride wins. And so the way we would rank these is like this. Let's go back to... Potassium for sure is the strongest. It's the second strongest on the chart. And then it would go chloride and then water. Chloride and water are out of order. But I would rank these as potassium, next chloride, next water. All right, then what we do is we copy the equations off the chart. I'm going to, so what we need to do is we need to reverse the potassium. I'm just going to write the equation from the chart here. And then what we'll have to do is we'll have to reverse that because potassium is our reactant. So the potassium metal will go to potassium ion plus an electron. And then for the water, I'm just going to copy it right off the chart. And so for water, we're going to have, let's see, 2H2O liquids is going to go to an O2 gas plus 4H plus 4 electrons. And so this is just copied off the chart, but I don't want to go back to the chart since I have these memorized. Okay, then we're going to just cross multiply. So I have 4 electrons here, 1 electron here, so I'm going to multiply this one by 4. And this one by 1, so just leave it alone. And so the net reaction here is going to be 4 potassium solids plus 2 water liquids is going to yield 4 potassium ions plus 4, oops, I forgot the, I think I screwed this up, unfortunately. Yeah, I screwed this up. I should have copied it off the chart here. I screwed it up because look at what I did here. I have 4 electrons as product here, and 4 electrons as product here. If both of these are giving up electrons, then who's taking the electrons? And so if one gives up, then the other has to take. And so here potassium's giving up, but I screwed up this. Here, for water. Water is going to take. And so what I did was I wrote the reduction one for water. I should have written the oxidation one for water. Water can be both. It can be an oxidizer and it could be a reducer. And so I'm going to do the oxidation one for water. 2H2O. And who's taking the electrons? The hydrogens are taking the electrons. So 2H2O plus, this is going to be 4 electrons. Recall that's 4 hydrogens. Yeah. This is going to yield H2 gas plus 2 hydroxides. Oh, I think I screwed up this. This should be 2 electrons. Let me just double check that this is balanced. So I have 4 hydrogens. 2 plus 2 is 4 hydrogens. 2 oxygens, 2 oxygens. Minus 2, minus 2. And so it's balanced. The electrons are absorbed in there. And so let me redo this. I wrote the wrong equation. This equation's on there on the chart, but I wrote the wrong one. And so this needs to be 2 instead. And so I'm going to get 2 potassium solids plus 2 H2O liquids plus 2 electrons yields 2 potassium plus 2 electrons plus H2 gas plus 2 hydroxides. All right, now I'm going to look for driving force. The driving force I'd like to assign off the half reaction. So this is my reducing agent. It gives up electrons. This will be my conjugate oxidizing agent. And so potassium is our reducing agent. Potassium ion is the conjugate oxidizing agent. And then water is going to be the oxidizing agent. And hydrogen and hydroxide, this will be the conjugate reducing agent. So hydrogen and hydroxide, the conjugate reducing agent. And I like to just compare the oxidizing agents. What's a stronger oxidizing agent? Potassium ion or water? And so we go back to the chart here, and we compare the two here. Potassium ion's here, water is up here. So water is a stronger oxidizing agent than potassium ion. And so we'll go back here, and then just write that here. Water is a stronger oxidizing agent than potassium. So this is driving force. I ran out of room. So cleaning this up, we're going to cancel out the electrons here. And that looks to be it. So the chart method predicts the correct reaction. And the correct reaction here is that we're going to have 2 potassiums plus 2 waters plus 2 waters. This is going to yield hydrogen gas plus 2 hydroxides plus 2 potassium ions. The driving force is not formation of a gas. Formation of a gas is only a driving force for metathesis. And so formation of a gas, formation of precipitate, we don't care in redox. Redox, we completely ignore all those other driving forces. We're only looking for stronger to weaker oxidizer or reducer. And so what happened to the sodium chloride? Do you see sodium chloride anywhere in this net reaction here? No, there's no sodium chloride. This was a trick question. Because you were led to believe that sodium chloride would react. It doesn't react. Sodium chloride is just a spectator. Do you see that? This is a trick question, but you know what happens if you get this? Then you could easily be fooled into doing single replacement. Do you guys remember skeleton redox here? In skeleton redox, we are given the major products. So we don't have to predict all the products. We just have to balance it, basically, because the major product's given. And so we balance each half reaction by balancing all elements other than hydrogen and oxygen. Balance oxygen by adding water. Balance H by adding H+. Balance electrons balance charge by adding electrons, and then combine them and simplify. And so these are the basics skeleton redox. And so the last question here is kind of a hybrid. This would be like an advanced because we've got to use multiple methods. And then we have to figure some other stuff out. And so the redox chart example, and we use experience, that is observations. And so let's take a look at this one. We're going to try the chart method here. We're going to use ethanol. Ethanol is CH3, CH2OH. Potassium permanganate, do you know the formula? KMNO4 is correct, good. And hydrochloric acid? What's the formula for hydrochloric acid? HCl. There is a potential metathesis reaction here. So if we do potassium permanganate and hydrochloric acid, we are going to form HMNO4. HMNO4 is called, well, it's permanganate. And if we convert it to an acid, we call it, permanganic acid. So we form permanganic acid and potassium chloride. And so there's a reaction here between these two. And these two are going to yield permanganic acid and potassium chloride. And there's a driving force for this. The driving force is stronger acid to weaker acid. And so we have metathesis reaction occur here. But is that it? No, what other types of reactions do we have? We have acid-base and redox. Is ethanol a very good acid or base? It has OH, but it's not hydroxide. And it's not really acidic or basic to any large extent. It's mildly acidic, but pH of we usually treat it as neutral. But what about redox? The reason I think of redox is because I think about permanganate. Permanganate is a powerful what? Oxidizer. It's like number 5 on the chart. Permanganate's a powerful oxidizer. So I'm thinking, if permanganate's present, what can it oxidize? Well, it could oxidize chloride. It could oxidize water. But is chloride and water very easy to oxidize? No, but you did. You did oxidize chloride. Remember that? You took solid potassium permanganate and mixed it with HCl, and you're supposed to generate chlorine gas. So chloride gets converted into chlorine gas. Do you remember doing that in lab? It's chloride's hard to oxidize, but we can oxidize it, and so that's why we oxidize to chlorine gas. However, what about ethanol? Is ethanol easy to oxidize or harder, even harder to oxidize? Because ethanol is not on a redox chart. And so if something doesn't occur on a redox chart, we can do two things. One, we could just ignore it. Maybe it's not very good, oxidizer or reducer. Or two, we could try to factor it in. I think, is ethanol easy to oxidize or difficult to oxidize? Let's say, is water easy to oxidize or difficult? So can you burn water easily, or is it difficult to burn water? Because burning is oxidizing, it's combustion. So is it hard to burn water or easy to burn water? It's hard. Have you ever tried to burn sodium chloride, salt, table salt? Does it catch on fire, or is it hard to catch on fire? It's hard to catch on fire. You could, potentially, burn water and burn sodium chloride, but it would be pretty extreme. How about ethanol? Is ethanol easy to burn or hard to burn? Ethanol is very easy to burn. It's highly flammable. You got to be very careful.
It's not a conductor.
It's not a conductor. Yes. It's a non-conductor. But it's easy to burn. And so the experience here is that this stuff is highly flammable. Have you ever heard of metal fires? Like lithium fire, metal fires? Metal fires are very dangerous because metals are potentially highly flammable. You know, when I was in the Boy Scouts, we'd go on backpacking trips and we'd bring steel wool. You know why we brought steel wool? To set the campfire, to light the campfire. You just catch the steel on fire and then it lights the wood on fire. And so used to use steel wool as an easy way to start campfires rather than gathering a whole bunch of twigs. But it's highly flammable and therefore it's a good reducing agent. But it's not on the chart. Potassium permanganate's on the chart. I mean, permanganate's on the chart. And so what we're going to do is we're going to inventory first. And so the major species here are ethanol, potassium ions, permanganate ions, hydrogen ions, chloride ions, and water. Ethanol is a reducing agent. It's electron rich. Potassium ions are an oxidizing agent. Permanganate with H plus is an oxidizing agent. And then H plus alone is an oxidizing agent. Chloride is a reducing agent. And water is both an oxidizing agent and a reducing agent. So we have 4 oxidizing agents. Out of these 4 oxidizing agents, which one is strongest? What do you guess? Permanganate. This would be the oxidizing agent I'd least I'd want to eat the least. Potassium ions, okay. You know, lots of people have potassium ions, sea salt. Water, no problem. A little bit of acid, okay. You know, lots of people like acid, vinegar, whatever in their food. But potassium permanganate, no, thank you. And so permanganate and acid will be our oxidizer. Which of these is easiest to burn? Chloride, water, or ethanol? Ethanol. We already determined that. And so the reaction should be here. Now, permanganate, I have the equation. I can just copy the equation off the chart. If I copy the equation off the chart, I have permanganate plus 8H plus 5 electrons yields Mn2 plus 4 H2O liquids. So I have that. But what about ethanol? I don't have that on the chart. And so for ethanol, we're going to use the skeleton method. When you burn ethanol, what do you form? Do you know? CO2. Actually, you don't necessarily have to form CO2. So this symbol's for oxidizer. So ethanol in our body gets oxidized to CH3CHO, ethanol, we call this. And then eventually it gets oxidized to CH3COOH, which is ethanoic acid or acetic acid. And then eventually it gets oxidized to, at the end, CO2. You can't oxidize carbon any further than CO2. So CO2 is the max. I told the Chem 4 class, I went on a camping trip to Joshua Tree. And there's the dollar store in Joshua Tree. And so I was in the dollar store and they had $1 bottles of Santa Barbara wine. So that, you know, $1 bottle of Santa Barbara wine, I'm going to buy it. So I have some wine at the campfire. And so I bought it and then took it back to the because I thought it was a bargain. So I took it to the campfire and opened it, and then I took one taste. Do you know what it tasted like? Yes. It tasted like acetic acid. It was so bad, I couldn't drink it. So that $1 bottle of wine turned out to be a very expensive fire extinguisher to put out the campfire. I was extremely disappointed. Yeah. What? Yeah, I know. What did I expect, right? It was stupid. But anyway, it would have been okay if all the ethanol were oxidized to CO2. I would have been happy. If all the ethanol were oxidized to CO2, then at least I'd have like sparkling grape juice or something like that, you know? But it was only partially oxidized. And so that was the big disappointment. And so this is partial oxidation. Fortunately, it wasn't to carbon monoxide, because if it were carbon monoxide, that would it be oxidized to carbon monoxide? I don't know. I'd rather have the vinegar than the carbon monoxide. But over here we have complete oxidation. And so what we're going to do is we're going to assume complete oxidation, which isn't a bad thing to assume because permanganate is a strong oxidizer. So assume complete oxidation. And therefore, all the ethanol should be converted to, not vinegar, but should be converted all the way to CO2. And now we're going to use the skeleton method to figure it out. So over here I have 2 carbons. Over here I have 1 carbon. So I got 2 carbons here, 1 carbon here. If they're mismatched, then what we do is we change the coefficient. And so I'm going to change the coefficient up here to 2. That's going to give me 2 carbons. All right, then over here I have 1 oxygen. Over here I have 2 oxygens. So 1 oxygen, 2 oxygens. And so I'm going to add 1 H2O over here. So plus an H2O. And then let's take a look at the hydrogens. Over here I have 3, 6, 8 hydrogens. Over here I have 0 hydrogens. So I'm going to go plus 8H plus. And then let's look at the charge. Over here I have 0 charge. Over here I have plus 8. So I'm going to have to do plus 8 negative charges, or 8 electrons here. And then add everything up. And so the reaction is going to be CH3CH2OH plus H2O liquid is going to produce 2 CO2 gas plus 8 H plus 8 electrons. And then I'm just going to double check if it's balanced. So 2 carbons, 6 hydrogens, 8 hydrogens, 8 hydrogens, 1 plus 2, 2 oxygens. I have 4 oxygens here. I didn't correctly balance it. Do you see I screwed up? So 2 oxygens here, 4 oxygens here. I screwed up the oxygen balance. And so I realized what I did. Do you see what I did? This turned out to be wrong. I miscounted the oxygens. Here, if I have 2 CO2s, I'm not going to have 2 oxygens. I'm going to have 4 oxygens. And therefore, this has to be 3 H2Os. All right, so let me try that again. If that's 3 H2Os, then I have 3, 6, 6 plus 6 is 12 hydrogens. And that means I need 12 H pluses. If I have 12 H pluses, I'll need 12 electrons. All right, so let me try this again. So it's going to be CH3, CH2, OH plus 3 H2O. It's going to yield 2 CO2s plus 12 H plus 12 electrons. All right, now let me double check this equation to make sure it's balanced. 2 carbons, 2 carbons. 6 plus 6 is 12 hydrogens. 12 hydrogens here. 4 oxygens, 4 oxygens. So the atoms are balanced, and then the charges should be balanced. 12, this is supposed to be plus 12 H plus. So plus 12 minus 12, it's balanced. So this is the balanced equation here. Then we're just going to cross multiply and combine. And so the permanganate, actually, what am I doing here? The permanganate takes 5 electrons. And this gives up 12 electrons. So I'm just going to cross multiply here. And so I multiplied the permanganate equation by 12, and then I'm going to multiply the ethanol equation by 5. Okay, then I'm just going to add everything up. Okay, then I'm going to look for driving force. The driving force I'm going to base on the half reaction. So this is my oxidizer. It's taking electrons here. And this will be the conjugate reducer here. Okay, this will be the reducer here. It's losing electrons here. And this would be the conjugate oxidizer here. And so I'm going from this oxidizer here to this oxidizer here. So I'm going to ask you this. This is going to be from experience or general observations. But what is a more powerful oxidizer? Permanganate or carbon dioxide? Permanganate. I mean, carbon dioxide we exhale with every breath. Do you worry about it, causing oxidative damage to your throat? Even if it stays in the lungs, it causes acid problems, but not oxidative damage problems. There's no driving force for it, actually. This is why CO2 is used. CO2's, even though it's like an oxidizer, there's fire extinguishers made out of CO2. CO2 is an oxidizer, and so it's like fanning the flames. If you're using a CO2 fire extinguisher on a paper fire, it's like fanning the flames, but CO2 is so weak, there's no driving force for it. Because it's going from CO2 to CO2. But anyway, so is there a driving force? Do you need the chart for this? No. Permanganate is going to be way stronger oxidizer than carbon dioxide. We don't worry about carbon dioxide being... Carbon dioxide is extremely weak oxidizer, and it doesn't even appear on our redox chart. But it is an oxidizer, nonetheless. So there's driving force for this, and that means the reducing agents must be the same. And so ethanol is easier to burn than manganese 2 ions. Manganese 2, to take the electrons from, ethanol is much easier. Ethanol is what we call electron rich. So let's simplify this. Simplifying this here, I have 96 and 60. I have 60 H pluses. I'm going to get rid of all those. And I'm going to get rid of 60 out of the 96, leaving me with 36. The 60 electrons, I'm going to get rid of those. And I have 15 waters here I'm going to get rid of, and I'll get rid of 15 out of the 48, so that's going to give me 33 waters left over here. And so it's going to come out to 12 permanganates plus 36 H plus 5 ethanols yields 12 manganese 2 plus 33 H2O liquids plus 10 CO2 gas. So in other words, we're going to use a very powerful oxidizer to oxidize ethanol all the way to CO2. And let's double check if it's still balanced. 12 manganese, 12 times 4 is 48 oxygens plus 5 is 53 oxygens. 33 plus 20 is 53 oxygens. 36 hydrogens plus 10 times 6 is 30. So 66 hydrogens. 33 times 2 is 66 hydrogens. And then oxygens we already did. So the atoms are balanced and the charge is balanced. So 12 times minus 1 is minus 12 plus 36 is plus 24. And then 12 times 2 is plus 24. So it's balanced. So this would be good. All right, any questions on this? All right, I'm going to stop talking here, and then why don't you go ahead and start on, what we're going to do is we're going to try to work on the redox equations from experiment 18. So start on those, and then you can get them checked off if you want. Eventually you're going to get them, oh shoot, I forgot to change the date on this.